So we're into chapter 3. We're really heading for understanding chemical reactions. Where we're going is maybe seeing something burning and going from seeing methane burning on your stove to going, well, how could we express that? How do we write the methane? What's the other chemical? It's oxygen. What products do we get? CO2 and water. And then how do we write a balanced equation using the formulas for the methane and oxygen and the CO2 and water, and balancing that the mass at the start equals the mass at the end, okay? Because we're not God, we can't make mass from nothing, okay? We have to follow the law of conservation of mass, and that's what we do when we balance equations. Okay? So that's our goal. It's going to take us about 3 days to get through all of that. First is just recognizing when a chemical reaction occurs before we start writing them tomorrow. So a few examples would be when you have a new color. So if you take 2 white powders, you mix them together, and everything stays white, well, maybe nothing happened. If you mix 2 white powders and all of a sudden there's a blue compound, something must have changed. That would be evidence of a chemical reaction. If you take solid copper metal, okay, and you put it into a reaction, does anybody know what color pure copper is? You should know. You see it. The Parliament buildings were copper. They turned green, but they were something at the very beginning, and then hopefully you've seen a penny before. Brown, okay? So if I put pure copper into a chemical solution, the pure copper is going to be brown. If that turns into copper ions because of a chemical reaction, these ions are a nice, beautiful blue color. So seeing the solid copper, a copper pipe, or I put a penny into a solution and I see the solution turning blue, that's a sign of a chemical reaction. Okay. Sorry, that's the second one. The first one was odor. You have a smell that's unique that you haven't seen before. I just talked about the color change as a second piece of evidence that you have a chemical reaction. Okay. You have a new gas, would be another piece of evidence or a different piece. I don't know if you remember, but I did a demo. I put some calcium metal into water, and it got hot, and you could see the bubbling and fizzing on the top. The calcium was a solid, and then I had liquid water. There was no gas at the beginning, but it made hydrogen gas during the chemical reaction. We saw those bubbles. So that'd be a sign there was a reaction. Another sign is the formation of a new solid or a precipitate. And we're about to dive into that one on the next slide and using the table. Okay. So you take 2 aqueous solutions, okay, that are, all the chemicals are totally dissolved. You mix them together and you get this bottom solid sitting on the bottom. Okay. Sign there's a chemical reaction. Okay. And last, if you feel an energy change, most likely temperature. You mix 2 chemicals and something got hot. Or you mix 2 chemicals and it gets really cold. You can go to maybe athletic stores or physio clinics and buy, you know, a pack that when you break it and the 2 chemicals mix together, it gets colder. So you can, you know, take it to your soccer game, and if you get you need a cold pack, you can mix the chemicals. Okay? Not a lot of reactions get colder. And we don't have any nice demos in high school, but lots of reactions get warmer. Okay. Okay. But you could also have light coming off, okay, or sound being created. Okay. Or in Chem 30, we'll do a whole unit when electricity is made. Okay. So you do a whole unit, we'll study reactions that one chemical loses electrons, the other gains some. Now, if you run a wire between those 2 chemicals, you make a whole circuit, that's a battery. If you run those electrons through a wire instead of them just going from one chemical right to the other. Okay? So these are all evidence of reactions, and in Wednesday we'll do, your next lab will focus on this. Okay? So how can you predict whether you're going to get a precipitate? And hopefully you have your formula sheet right on your desk, and you don't have the periodic table side up. You've got the back side, and you're going to see a table similar to this. I don't think it's identical. Yeah. Very similar, just the columns are in different places. This is the one I believe from your textbook. Okay. We want to predict the solubility of ionic compounds. In Science 10, you get one table. Next year, you're going to use this is the exact version that's in your Chem 2030 data booklet. Okay. This, so you're not going to take this table down, but I'm going to explain it. You may want to make some notes in your book of how to use this, and this is all going to go in D2L, what I'm about to write. And then you'll write the examples down below. Okay. This table lets us predict whether a pairing is highly soluble in water. And if it is, we write aqueous. I don't have to write out highly soluble. Chemists want short forms. That's really all we're doing. I don't want to have to write sodium chloride. I want to go NaCl. Okay. I don't want to have to say in water. I want to be able to write aqueous if it's nicely dissolved. Okay. So anytime we end up in this first row, not counting the headings, it's a highly soluble or aqueous short form. Okay. If we end up in the bottom row, these have low solubility, the pairing of the positive and negative ion have low solubility, and we're going to write solid. They don't dissolve. That'll be a solid chunk sitting on the bottom. And I'm going to jump into some examples because I really need an example to explain this. Okay. What happens if we put each of these four solids in water? We're going to predict whether they're going to stay together as a solid and just fall to the bottom, which would be low solubility, or whether we put it in solution and whether the water can break it up. And we're going to write aqueous because all the ions are separated. So the only weird thing about this is start with the negative ion first. That's how the table's built. If you remember that, you're going to be fine. So in sodium chloride, the negative ion is always the second piece, and in this case, it's the Cl minus. So I have to find Cl minus in my table. There's the chloride. Okay. Then I'm going to go down to find the row that represents the positive ion. Okay. So chloride with most positive ions is going to be highly soluble, except if that positive ion is silver plus, lead 2 plus, copper plus, mercury plus, or I think Tl is thallium, but I could be wrong on that, thallium plus. Now, we have sodium, so no, none of those are sodium, so sodium would fit under the most. So chloride with most things, including sodium, is going to be highly soluble. So if you put sodium chloride in water, we're going to write it as NaCl aqueous. Okay. Okay. So up above, I wrote solid. These are solids we're going to put into water and see what happens. Okay. Does it form a precipitate or stay a solid? And it doesn't matter whether you put NaCl into solution or you dump in chloride in one compound and sodium in another and they come together. Okay. We're predicting even if they try to come together, they would still stay aqueous, they'd stay separate. Okay. So sodium chloride in a solution will be dissolved. Second example is calcium chloride. Okay. We see three different types of elements. We've got calcium, we've got carbon, we've got oxygen. Okay. But ionic compounds always have two ions. You've got to figure out how to break this up. And your default would be, well, it's probably a metal and something else. And I see that metal. Okay. We've got calcium, so that must be the split. I've got calcium 2 plus, and this carbonate, the CO3 is 2 minus. And the CO3 is in your data booklet, the name and the charge if you're not sure. But calcium is group 2, it's plus 2. Okay. So we have to start with the carbonate. Okay. Carbonate is the negative ion. Okay. Never try to break things in three pieces. It's always positive and negative. So carbonate. So there's carbonate. It's in with the phosphate and sulfite. So carbonate with anything in group 1 would be highly soluble. Is calcium in group 1? No, it's a group 2. It's an alkaline earth metal. So we're not there. It's not paired with NH4. We're not that. So we have carbonate paired up with most things. Okay? Everything other than those is lumped under the most. And it's going to be a solid. Okay? You put calcium carbonate solid in water, or you make it, it's going to be solid no matter what. Water is not powerful enough to break up. Okay? So in water, calcium carbonate, we still write it as a solid. It's going to be a heterogeneous mixture. There's going to be 2 layers, a solid layer on the bottom and a aqueous water layer on top. Silver chloride. I've got another chloride. So I've got to start with the negative ion first. There's only 2, so the first one's the positive, the second one's the negative. So there's chloride again. Got to go down. Most things with chlorides are aqueous, except for, I've got silver right in the table now. Chloride paired with silver is going to be a solid. Okay. So silver chloride in water or formed in water will not dissolve. Your conductivity, the light would either barely turn on or not turn on. This is low solubility, so maybe 1 in 1,000 dissolves, okay? But very little. Okay? We write solid. Last one, copper chloride, okay? Which is not the correct name. Can anybody tell me what the right name for this guy is? And then I'll go and figure out whether he's soluble. So don't say it yet. I want to make sure everybody's going to think. Okay, so the question is first of all, you have to figure out what I'm leaving out. Because the copper chloride isn't wrong, it's just incomplete. You want to make a stab at it? 2, yeah, and you can just say 2. That is copper 2 chloride. There's 2 types of copper, so you have to write or say the 2, and we don't use the number 2, we use the Roman numeral. This is 2 plus, and that's minus. Chloride is always -1, and there's 2 of them, so this has to be the +2 type. The charges totally matter. Right here it says Cu plus. Okay? Chemists are lazy, we don't like to write 1s. Okay? You keep seeing me make that mistake. In Science 10, your data booklets have 1 minus. Next year, they'll just say minus. Anytime you have a -1 or a +1, we just drop the 1. The same way that we don't write when there's 1 copper, we don't put that 1 in, we drop it. Your booklet is doing this. This is copper +1. That is copper +2. They're totally different. Okay? So we're going to ignore that copper. So chloride with copper 2 plus. There's chloride. It's soluble with most things except for silver plus. We don't have that. Lead 2 plus. Well, it's not that. Copper +1. No, we have copper +2. That's different. And mercury, and I think that's thallium, though I'm not sure. Okay? So copper 2 would fit under the most and is highly soluble. So CuCl2, copper 2 chloride is aqueous, is highly soluble. So you've got to watch those multivalent transition metals. Iron has a couple forms, cobalt has a couple forms. We just did copper has a few forms. Manganese has several. Chromium has many. I think your table lists 2, but there's at least 2 or 3 more different types. Okay? So that's just your warning with the charges. There's lead 2 plus, but there's also a lead 4 plus. So don't just see, oh, PB, that's lead, there it is. Keep going, watch the charge and make sure you're correct. So that's using the table to predict whether something is very soluble or has just a little bit of solubility. And that's as far as you're going to go in high school with this. In Chem 20, you'll get this as a review lesson again. In Chem 30, you'll get another review lesson. Regular Alberta curriculum, you just do high or low. If you choose to take AP chemistry, we learn how to do the math of that says low. Well, how much do you get? We actually do the calculations of what is that little bit, and we'll put a number to it. Last, before leaving this, just giving you a visual of what do I mean by NaCl aqueous. Okay, because this is actually really trying to almost convey a lie. You write NaClAQ, and anybody would think, well, wouldn't the Na and the Cl be touching each other? Like, that's how I just wrote it. And it's not true at all. And it's really easy to lose that. Okay? This aqueous means that this ionic compound is both dissolved and split up into its ions. Okay? So you don't normally write what I'm about to write, but it's very crucial you realize it. Okay? So I will not ask you to do this picture on a test. Okay? But the best way to convey this is we're going to have NaCl plus, and it's going to be surrounded by water. Okay? We're going to have the oxygen end of water towards it because that's the negative end. And I'm doing a 2D projection. In 3 dimensions, there'd be a water in front and there'd be a water behind the board. So we got a sodium ion surrounded by water. Okay? And we're going to have chloride ions. Okay? One of them at a time, and this is going to have the H side of water next to it, because that's the positive side of water. So we got a chloride ion. It's totally separate from the sodium. The sodium surrounded by water, the chloride surrounded by water. So if we had, 1,000 sodium ions, they're all separate. They're all surrounded by water. Okay? That's the best meaning of NaCl aqueous. I'm not going to draw out this one. Calcium carbonate solid. Now they're all together. And you've got a calcium and then a carbonate, then a calcium, then a carbonate, a calcium, then a carbonate. It's just that repeating pattern over and over again, and it's all stuck together. So as chemists, we're always using short forms. This one kind of makes total sense. They're together in a solid. This one you really have to realize they're not together. It's too big a pain. We don't want to have to write sodium plus aqueous plus chloride minus aqueous. We always put them together. Okay. So that's, we've really finished up going through predicting whether something is going to be ionic and conductive because it did break apart, aqueous, or whether we have it insoluble, we have a precipitate, and we're going to write solid. So we've completed this most of our recognizing chemical reactions lesson. We can now predict when something is going to form a solid and be a precipitate if it's ionic. Okay. Last, I just want to address energy changes, and we will be done for this lesson. Okay. We want to break down energy changes into 2 separate pieces, and they always occur in pairs. If there's a chemical reaction, we have to break some bonds. Okay? That's just always, if you start with some material at the beginning, you've got new things at the end, you had to break some chemical bonds. That always requires energy. If something's stuck together and you want to get it apart, you need energy to get them apart. And I use magnets as an analogy for bond breaking. If you have 2 magnets together, do you need energy to take them apart, or do you just get free energy when they come apart? Okay. You need to put energy in to rip magnets apart. Okay. So imagine I had a water molecule and I run a reaction and I end up getting some hydrogen gas. Okay, this isn't a full reaction, this is pieces. In order to get the hydrogens, two hydrogens together, well, you have to break this bond between the hydrogen and the oxygen. Okay? That always requires energy. Okay? So generally, in the beginning of the reaction, you're breaking things apart, and then you make new bonds. Okay? And you always get energy back. And this is a little less intuitive, that when you make new bonds, you always get energy. But I use the magnet analogy again. If I have two magnets and I just hold them apart, and I let go, they just come together spontaneously. Okay? They may flip themselves around, so north and south align, but if I have two magnets and I just let them go, they spontaneously snap together. You don't need any energy. You actually get energy back in the process. So you need energy to rip apart. You get energy back when things come together. Okay. One of these processes will be bigger. In most reactions, you put a little bit of energy in and you get more back, and you end up with a hotter surroundings. When you burn something, you need a little bit of energy to break the fuel up, and then you get a whole bunch of energy back when CO2 and water is made when you burn something. Very few reactions require a lot of energy and you only get a little bit back. The reason for that is most reactions that require a lot of energy and give you a little bit back just don't happen. They require too much energy and they don't occur. Okay? So we've got these two competing processes. Overall, one of the two will be larger in magnitude. So I'm going to make up some numbers to help this discussion. Maybe I have a reaction and I need 10 joules to get all the pieces broken up. And after they come back together as new compounds, maybe I get 100 joules released. So I need 10, I get 100 back. At the end, there would be 90 extra joules put out. I get 10 back, 10 were needed. 90 are just going to come out as thermal energy or heat that we can feel. Okay? And that's this. I'm almost done. I got 2 bullets left, and that would be this. If energy is released overall, so that's my green numbers. In that example, there's positive 90 joules released. Okay? 10 were used up, 100 released. The difference is 90. Okay? And the released is bigger. Okay, the bond forming is bigger. Okay. If energy is released overall, we call that reaction exothermic. Okay. I don't know if you've seen exo and endo in science already, but they're used all the time. Biology uses them way more than chemistry. Okay. Exo is always out and endo is always in. Okay. And again, you'll see that all over biology class. Okay. Thermic is heat energy. So heat, exo's out, and heat coming out, exothermic. Okay? We could have the other way around. Okay? Maybe 50 joules are needed to get the chemicals to come apart, okay? But you only get 40 joules back when the chemicals recombine. Okay? That, we needed 10 more than we got. Energy is going to be absorbed. Okay? It has to steal 10 extra joules from the surrounding. So if I'm right next to that reaction and the heat is stolen from me, I'm going to feel cold because it took energy from me. Okay? And that's endothermic. If energy is absorbed, okay, more energy was required than was released overall, we call that endothermic. So we've got that endo, in, heat in, to get the reaction to occur. And this bottom blue would be cold packs that you snap the chemicals, they combine together, and they need energy. So you stick it on your back and it sucks energy out of your back, thermal energy out of your back to run the reaction, and you feel cold, okay? Because it's the blue, okay? The difference, the 10 joule difference is coming out of your back in that cold pack. Okay. And that, okay. And again, this connection is all going back to if you notice a temperature change in a after you've mixed two chemicals, that's a sign there was a chemical reaction, there was a chemical process going on. Okay. So that concludes our first lesson in chapter 3. Okay. This will not be on your quiz tomorrow. So these are some questions you can work on